The roller coaster problem isn't so terribly difficult, but it tended to be one that trips you guys up. And if you've looked at your homework, you know that a bunch of the homework questions had to do with the roller coaster question. Just between you and I, here, sixth period, is the homework assignment too long? I have no kind of feel for it. So my APC class, they thought the homework assignment was too long. Let me rephrase this. I am not trying to change the level of work I'm expecting from you guys at home. So, we're in class each day. To me, that should be effectively a lot of our time. So I'm expecting the homework to be about an hour to an hour and a half a week, just like it's supposed to be. So if it's more than that, or what you feel is substantially more than that, I'm expecting you to let me know, not whine about it and jump on, yeah, it's too much work. But what you should not be seeing from me is me piling on busy work or anything like that. I'm trying to keep the same kind of level of work I would expect, but we're in review now, so I'm kind of picking particular topics and putting together questions, and are all coming from my AP. I don't have the same feel for how long it takes to do some of my AP questions versus the others. So if you think that, it is a bit too long or something, let me know on Slack. I'm willing to be flexible about due dates and all that kind of stuff, because, we are living in the dream, in the apocalypse here. So, ready to get started? All right. So I want to start out with a problem that is actually not a roller coaster question, but has all of the hallmark pieces of a roller coaster question. So, I say roller coaster problem, but what I really mean is this certain style of question that tends to get asked on these kinds of physics exams. So I want you to imagine I have a box that is, say, 1.2 meters away from a pivot point. It's connected to the pivot point by some kind of string, and maybe the box has a mass of 0.5 kilograms. And I'm going to release the box so that the box swings downwards like a pendulum. And at the bottom has some clear velocity. Now, you might be asking yourself, how is this a roller coaster question? Well, this isn't. But the question that tends to be asked about this is a question that comes at you sideways. It's not necessarily what you would expect. A question like this often will be about tension. A question where they ask about the tension in the cord holding the object at the bottom. And when I say roller coaster problem, what I tend to be talking about is a problem that combines together three disparate parts of our curriculum. The first one, and the one that I hope is the most obvious here, is that you should be seeing something that has to do with conservation of energy. This problem should show a clear relationship between the potential energy the object has here at the start and kinetic energy the object's going to have down here when it makes it to its lowest position. So it would probably be not unusual to expect that you'd be asked to figure out the velocity of the object. But when they ask for the tension, that clearly probably brings up net force. That this problem has something to do with net force and Newton's laws. But also, these problems oftentimes have something that brings together both the conservation of energy part and the net force part, and that's UCM, uniform circular motion. Because these problems often involve centripetal acceleration. So when I say roller coaster problem, I'm really talking about a whole classifications of problems where there is circular motion related to conservation of energy and net force. Now, in looking at these questions, they can really come at you from a lot of different perspectives. One of the things that I really want you to be identifying in any problem that you are given is to fully notice whenever you see an object traveling in a circular path. Take clear note of that, and it should send off all sorts of alarm bells. Because anytime we see an object traveling in a circular path, we know that there has to be several conditions in order for it to travel in that path. Let me be very clear. Any object traveling in a circular path must have an unbalanced force. That net force has to be towards the center of motion. And that unbalanced force must be proportional to mv squared over r. That the only way an object can travel in a circular path is if those conditions are met. So when you ask, or you are being asked about the tension in a problem like this, we're first trying to see, do you understand that the tension has to be more than the weight? The tension can't just be the weight. And a lot of people don't see it that way. But whenever there's an whenever an object's traveling in a circle, that should immediately be called into your consciousness. That the only way an object travels in a circle is if the forces are unbalanced. Now, I do want to walk through this question a little bit as a starting point for our roller coaster problems. And the reason I do is because it has some simplifications and there's no conditions on this problem. You'll understand what I mean about conditions in a minute. But the first thing I hope most of you recognize is that we have gravitational potential energy here, equivalent to mgh. And in the participant window, give me a yes or a no if you know what number you would put in for h. The height already here. The object's lowest position is down here. So the length of the string, this 1.2 meters, is going to serve as the height of the object. Now, it shouldn't take too much for you to realize that at the bottom of the swing, all of the energy is in the form of kinetic energy. 1/2 mv squared. But our goal is to find the tension. And the reason I bring that up is net force has to equal mv squared over r. And in this case, the r is the height. It's the length of the string. In fact, for the time being, I'm going to erase that r and put L here for the length of the string. And I recognize that there are two forces acting on my object. There's the tension, which acts upwards, which I'm going to make positive. Something to put in your notes, something that you should probably put whenever we're talking about net force. The positive direction should be towards the center of the circle, regardless of what's happening. The center of the circle, the center of the turn should be the positive direction. That way, T minus mg equals mv squared over L. Now, for a lot of you, you see a pathway to figure out the tension, but not all of you. So let's help with that pathway. We know that we could use the gravitational potential energy to help us figure out the velocity. We know that we're going to substitute in the centripetal acceleration in the net force. So it should be somewhat clear to you that our goal is probably to use energy to figure out the velocity, which we could then use to figure out the net force. But you'd be a fool to think that's the best way to do this. And I don't mean that to be mean. I mean that half of why we do the review isn't just about reminding you about stuff you already know. But part of the reason we do the review is to show that you can be more efficient sometimes if you have an idea of where the problem is already going. Remember, we're going to be under a time constraint, and you guys love to throw the numbers in. In fact, just watching a bunch of you, I know you guys are running out there and you're getting the answers. But if you're only interested in the tension, realize that finding the velocity is unnecessary. I mean, just pay a little attention to this. I'm going to take a look at this part right here for just a minute. And the first thing I'm going to do is I'm going to multiply both sides by 2. So I have 2mgl equals mv squared. Now, yeah, I could cancel out the m's. I sure could. But instead, I'm going to divide both sides by L. And I'll get 2mg equals mv squared over L. Now, the reason I'm doing that should be obvious. Look, I looked over here and saw the mv squared. I recognize there's an mv squared in kinetic energy. And I also saw that I had the L here in mgh. There's no reason to find the velocity unless I'm actually being asked for it, when the truth is, I can make my problem perhaps much more efficient if I recognize that there are shortcuts here. Ways to figure out the tension that allow me to be more efficient for the test. Now, you can't tell me that it's not much easier to do the problem that way than it would be to find the velocity by taking the square root, then taking it and square that again and putting all those numbers in there, where you can make a lot more mistakes in transferring from your calculator to your sheet and back to your calculator and back to the sheet. Do you see what I mean? And do you see how we can sometimes be more efficient by doing it this way? Well, I hope so, because we're going to move on to the actual roller coaster question, unless you guys have questions about this. In this question as well, that we could easily throw in a little bit of simple harmonic motion, right? Follow-up question B, what's the period of the system, garbage like that. So be aware that having a problem like this is not going to be just about the tension. They're going to throw in other stuff as well. Now, the reason why I wanted to use an introductory question first is because the roller coaster question is often asked as a conditional question. The last question wasn't. The last question was what I would call as procedural. Find the period. Find the tension. And you do realize, but the roller coaster question tends to be a conditional, but also there tends to be more than one kind of roller coaster question. So I'm going to divide the screen here in half, and we're going to talk about two different types of roller coaster questions. But the one thing that almost all roller coasters share is they tend to share that the roller coaster itself is built off of the ground a certain amount. So there's the ground. And I'm going to put problem type A over here and problem type B over here. And I say that they're two different types, but understand that they're the same problem. But there are different kinds of roller coasters. Now, there's my favorite, and my favorite roller coasters almost always have the same kind of elements in them. I love roller coasters that have a loop in them. I like the upside down part. So when I was filming your video, by the way, back to work. So this is the one I think you're expecting, is the roller coaster problem where we have the loop. But don't forget there's also other kinds of roller coasters. Now, this one doesn't look like the same kind of problem, but they really are both the same exact idea. Generally, in both of these problems, the car is placed, somewhere on the track. Oftentimes, they don't tell you. It's some height above the ground or some height above the lowest point. But these problems are often about a condition. Meaning, I think we know that in the track with the loop, that the car is eventually going to have to make it to the top of this loop. But there's a condition that has to be met in order for the car to successfully navigate the loop. And if you guys remember what we talked about when we came to this problem originally, we know that the car is 2 radii above the ground. So we understand that if there's gravitational potential energy here, that the only way the car will make it to this height is if we start the car at least that high above the ground. But we'd be wrong in assuming that we could start the car at the same height on the track here. Because the car not only has to make it to that point, but it has to make it with a velocity fast enough for it to stay in uniform circular motion. There's a condition to the problem. And that's what I mean by calling this problem a conditional. That we can't just start the car at any height, but we have to start the car in such a way that the conditions for uniform circular motion are still met. We have a similar problem over here, that the car can make it to this part of the track. But if we want the car to stay on the track and not jump off the track, we have to realize that the car is also traveling in a circular path, and therefore there is a condition on the car in order to maintain uniform circular motion. These conditional problems are tough because understanding the condition that allows for the car to successfully navigate the track isn't always the same and can be changed, and we can get problems that are outside of these boundaries. So we start with these problems because these problems at least we've seen before and help us understand what it means to be a conditional problem. For example, let's take a look at the loop-the-loop problem. In this problem, we understand that there are 2 forces acting on the car when it makes it to the top of the track. First, the car has weight. That's not going to change. But the car also is touching the track, which means the car is experiencing a normal force from the track. Now, as I said just a moment ago, for any problem where we have a circular motion as part of our problem, making towards the center of our loop the positive direction is very important. So I'm making that direction positive, which automatically suggests that mg and the normal force are both in the positive direction. But they're traveling in a circle, so this net force has to equal mv squared over r. This is my net force equation. But there's an important implication here. We know that v is going to be the result of conservation of energy. Meaning the velocity we get there is because the car was acted on by gravity. And we can figure out how fast it's going by comparing the height it started to the height it attains. That's completely separate from dealing with force. But we know that the velocity is tied in to the conservation of energy. At the same time, the weight of the car doesn't change. Neither does the radius of the track. Neither does the mass of the car. These variables are fixed when the car is released. However, we can decide how fast the car is going by choosing a height. We make the car faster, we'll need more normal force in order for the car to stay in a circle. The track has to push down harder. But if I want the car to go slower, I understand that I have a limit to how slow the car can go. Because if I go too slow, I reach a point where the normal force is going to approach 0. If I try to go any slower than that, the right side of this equation will be less than the left side of the equation, and the car won't travel in a circle any longer. It'll just fall. It'll be a projectile. It won't be in circular motion. Meaning the car will make it maybe not as high and will fall away from the track. It's a conditional. What is the minimum speed the car has to travel to stay on the track? That's the condition. And that's understanding that that minimum speed occurs as the normal force approaches 0. We have a similar conditional on the other side. On the other side, the center of the track is beneath the car. but we still make that direction positive. So I have two forces acting on the car again, mg and normal. I'm still going to make towards the center of the track, the positive direction. So mg is positive, but normal force is now negative. This is still going to be equal to mv squared over r, but now things are a little different. I understand that if the car wasn't moving at all, it would just be in contact with the track. That's no big deal. But as the car begins to go faster and faster and faster, as v begins to increase, well, it can continue to increase. I just will have less and less normal force. I mean, we could consider solving this for normal force if it makes you feel better. By putting it like this, you realize that this number is fixed, doesn't change. But the faster the car goes, the more I'm subtracting this term from the weight. The limit, the condition, is when the normal force goes to 0. I can't go any faster than that, or else all of a sudden I need a negative normal force. I need the track to pull down on the car. Now, if it's a roller coaster, that's possible. If it's the street, you just got airborne. And you went from being a person driving on the street to a person who's now in a car that's a projectile. Now, tomorrow we're going to dive into the meat of this. But before tomorrow's class, please make sure you watch the video I'm going to post, because it's only about 12 minutes, but it really shows off what happens when the condition isn't met. And that's what I want you to be able to see. All right? So that's it for today. It's been awesome seeing all of you guys. I really appreciate seeing you here today. And today, because I've been watching the clock a little bit closer and making sure we're on